The new Levante high-speed railway line is a key part of Spain's strategic infrastructure and transport plan 2006 to 2020, which is developed by ADIF, the country's railway infrastructure manager. The line is more than 914 kilometers long, and a total of 12.4 billion euros will be invested in the project. Furthermore, the route is one of the most difficult in terms of construction, and some sections of the line represent a real challenge for Spanish engineers. One example of such a challenge is the section between the Contreras Reservoir and Villargordo del Cabriel, which passes through the municipalities of Minglanilla in the province of Cuenca and Villargordo del Cabriel in the province of Valencia. The section runs from west to east along the same corridor as Spain's A3 highway. San Jose is constructing the section of the track between the Contreras Reservoir and Villargordo del Cabriel. This section is without a doubt the flagship section of the Levante high-speed railway line. It's one of the most difficult sections of railway that is being built in Spain in technical terms, because over the course of just 6,524 meters, the track has to pass through 3 tunnels and cross 3 viaducts, 85% of the section as a whole. 2 of these structures are record breakers, either in terms of their length or their height. This technical complexity is a result both of the area's rugged landscape and of the need to avoid damaging the nearby Oces del Cabriel Nature Reserve. The section between the Contreras Reservoir and Villargordo del Cabriel begins at the Olla de la Roda tunnel, which is 2,000 meters long. This tunnel, like the Rabo de la Sartén tunnel, which is 390 meters long, and the Umbria tunnel, which is 1,500 meters long, was dug out using mechanical tools and, in some sections, rock blasting techniques. The new Austrian tunneling method was used to construct all 3 tunnels. Although it is the shortest tunnel along this section of the line, the Rabo de la Sartén tunnel poses particular difficulties because it runs alongside the A3 highway, and in some parts the 2 tunnels are just 10 meters apart. This means that the tunnel has to be excavated using controlled blasting, and sounding equipment needs to be used in the existing tunnel to ensure that it is not affected by any vibrations. The viaducts in this section of the line significantly reduce the distance that the track needs to cross over valley bottoms and dips. The first viaduct that the line crosses if travelling from Madrid is the Cuesta Negra viaduct. It is the smallest of the 3 viaducts, but is still 220 meters long with 19 meters high piers. The Istmo viaduct is 830 meters long, making it the longest of the 3 and 70 meters high. Each of its spans is 66 meters wide, and it is the largest constant thickness slab built using a movable scaffolding system in Spain. The viaduct over the Contreras Reservoir is 587 meters long. It is a concrete arch viaduct with an upper slab along which trains can run. This is the most spectacular structure of the project, particularly because it has an arch span of 261 meters, making it the longest viaduct of its type in Europe. In order to complete this unique project, San Jose has had to make use of major technological developments and a combination of the most advanced and innovative construction systems available today. The project is highly complex because it uses a series of different construction systems to build a single structure: movable falsework, arched falsework, and a series of braced sections. Furthermore, a series of temporary 40 meters high piers need to be constructed and later demolished once the project is complete. Each of these temporary hollow core supports are made using a self-climbing formwork system, similar to the one used to make the viaduct's permanent piers. The arch spring is constructed by first placing arched falsework directly on the ground. The arch formwork is then assembled on top of the upper metal part of this falsework. Once this formwork is in place, the first hollow section of the arch is concreted. The permanent piers are built onto the constructed arch, and the construction process follows the same procedure as the one followed in the rest of the viaduct in the approach zone. The upper slab, which consists of a pre-stressed concrete box girder, is built using a movable falsework system, following the classic procedure. The slab comes to an end when it reaches the land next to the reservoir. A metal pylon is erected on the slab. This pylon must be able to anchor the top of a provisional bracing system, which is then used during the most important stage of the construction of the arch. The arch above the reservoir is concreted using a system consisting of a mobile metal cart, on top of which a formwork structure is erected. The viaduct will be built in stages, at a rate of 1 3 meters long section per week. Advancing cantilever construction requires a series of braces hung from a metal pylon. The number of braces required increases gradually as the arch is concreted. Once the arch has been constructed and the crown has been closed, the entire temporary system of braces and metal pylons is removed. Hydraulic jacks, which can physically lift the arch, are used to remove the arch supports on the temporary pier. These jacks make it possible to remove any temporary support equipment. The temporary pier is then demolished. Once the temporary supports are removed from the concrete arch, the rest of the structure is built. The Contreras Viaduct strikes a perfect balance between functionality and design, and is therefore an excellent example of the high quality of engineering in Spain, and of the construction skills of a company such as SANJOSE. Finally, it's worth highlighting that, as a result of the unique nature of the natural environment surrounding the site, the construction process has been adapted to the nesting seasons of local birds, and the construction techniques used have been selected to keep any environmental impact to a minimum.